What's up, my chemistry students? I hope you are ready for today because today we are calculating heating and cooling curve problems. Actually, we're just going over heating problems, so I'm taking it easy on you. All right, so you need to draw this graph and you need to write all of these values. And so what you see here are different specific heats. And you learned before that specific heats are different for each substance, but what we haven't learned is that they're even different for which state of matter you have it in. And so here I have the specific heat of water, but in all three of its phases, as ice, as water, liquid water, and as steam. The other thing that I have here is the delta H of fusion and delta H of vaporization. And so we'll do some calculations with those. All right, so here is my graph, and we're going to label it again. I'm going to use a couple of colors. And so something you need to know is that we are going to use Q equals MC delta T a lot. And so let's write that here. Q equals MC delta T. You're going to use Q equals MC delta T for every single diagonal line that you have to calculate. So on the diagonals, when temperature is changing. So that means at segment 1, at segment 2, 3, remember this is 2, that's 3, 4, and at segment 5. So that's when we're using Q equals MC delta T. All right, we actually have a different calculation to use when we are on the plateaus. And so what do we use? We use enthalpy stoichiometry. Let's write that, enthalpy stoich, when the lines are flat. So on the plateaus. So what does that mean? That means that yes, you do have a calculation to do for every single line segment. Remember that there are 5 of them. It just depends on the problem whether or not you have to do all 5. So what you need for enthalpy stoichiometry on the flat lines are these values. Remember that this bottom line is going to be melting from solid to liquid. Instead of the word melting, it's delta H of fusion, F-U-S for fusion. Okay, and then at the top, we have delta H of vaporization that we'll be utilizing in order to solve problems here. Okay, you have to remember at what temperature, that's not good, at what temperature will this be happening? You still need to remember that for water, or whatever graph you're doing, this is going to be 0, and that's going to be 100. Okay. The specific heats that you're using, so each one of these C's are different, so be careful. When you're solving these problems, you're not doing it for the same C. They're 2.03, 4.184, steam and ice are pretty close, but there's a huge difference when you're looking at water. This is at the solid state, so you will use the specific heat of the solid, here the liquid or water, and here steam or gas, which is just steam. Okay. Let's see. Let's try our first example. So please write this down. It says how much heat is needed to convert 50 grams of water from 70 degrees Celsius to steam at 110 degrees Celsius. Every time you do these problems, I want you to draw a little mini graph. And I want you to draw the entire graph, even if you're not using the entire graph. So here it is. Here's my little mini graph. Doesn't have to be perfect or beautiful. There it is. Quick diagonal lines. I'm going to label the temperatures 0, 100. Okay. I'm also going to label the temperatures on here. So where am I starting on this graph and where do I need to end up? Now, it doesn't really matter if you get the scale right. You just have to show that it's within the ranges of temperature here. So it says we're going from 70. So it's going to be about right here. Like I said, that doesn't really matter. So you're starting here, and you're going to 110 degrees C. So that's somewhere up here. I know my scale is off, but I want to be able to show that this is a different line segment. So the number of line segments that you have within that range, that's the number of calculations that you have to do. Okay, so for us, for this segment from here to where it changes, to where it curves, that's 1. From here to here, the flat part of the line, that's 2. And then this little segment right there, that's 3. So there's 3 calculations that I have to do for this problem. All right. Remember that we must draw this. In fact, you will lose points if you are not drawing the little mini graph. All right. We need to figure out delta T for each one of the times where our temperature is changing. And so this is going from 70 to 100. Be careful. We need to worry about sig figs here. So from here to here, it's going from 70, so that's initial, to 100. So 100 is final. Now I'm going to use the same number of places that's given in the problem because we defined 100 as the boiling point. So we want that we can put as many zeros as we need. So we're going to put the same number of zeros after as it has here. So that's 100 degrees minus 70 degrees gives me 30 degrees Celsius. Okay, so it increased in temperature by 30 here. What about this little line segment right here? From here to here, well, it ends up at 110, 110.0, and then it goes to, or excuse me, it came from 100, so that's minus 100 degrees. Okay, and that would just be a difference of 10 degrees Celsius. But notice I have 3 significant figures here. I wouldn't want that to just be one sig fig. All right, so we'll do our first calculation. So here we are at a diagonal line. So let's just label that 1 for calculation 1. At a diagonal line, okay, thank you. At a diagonal line, you are doing Q equals MC delta T. Okay. So here we go. We're going to use Q equals MC delta T. The mass is 50 grams. Times C. I have 3 different C's. Which C do I use? Well, I use the C that's for this part of the graph right here, which is water. So that's 4.184 joules per gram degrees Celsius. Okay, and then the temperature change for this little segment here is 30 degrees. Okay, do not be tempted to do the entire temperature change. We're only looking at the segment, which is why you have to draw this. Okay, so then we'll cancel units and then solve, and I get Q is equal to 6,280 joules. I'm going to make a note that this specific heat I used here is C for water. Okay, because it was in the liquid state, it was in this segment right here in the middle. Another thing that I want you to do is I want you to make a note that when you have joules, you're going to convert those into kilojoules, and you'll see why. So at the top, I'm just going to write this, change answers to kilojoules. Okay, and the conversion for that, remember, is 1 kilojoule is equal to 1,000 joules, something you have to have memorized. Okay, so make that little note at the top. All right, so there we've gotten through that segment, but I just told you you need to convert to kilojoules, so let's do that. So we've got 6,280 joules. I would like you to show the work to do this. Okay, so 1 kilojoule is 1,000 joules. And so that just becomes 6.28 kilojoules. Put a box around it. All right, let's do line segment number 2. That's a flat line. That's a plateau. And the flat lines, you are using enthalpy stoichiometry. So let's do that. Actually, which flat line is this? Do I use enthalpy fusion or vaporization? Well, I'm at the top, so I'm going to use vaporization. All right, so here we go. Number 2. You'll just start out with the mass of water. Remember, all of these, even though they're ice, steam, water, they're all H2O. So 1 mole of water is 18.02 grams. And then we need the delta H of vaporization, which is 40.7 kilojoules for every mole. Okay, grams cancel, moles water cancel, and we get 113 kilojoules. Okay, this is why we have to have this answer in kilojoules, because we're actually going to find the total amount of energy. So we'll have energy for each line segment and then add them together, so they need to be in the same unit, so kilojoules. All right, number 3. Number 3 is this little tiny line segment right here. So it's a diagonal, which means we're going to use Q equals MC delta T. It's at the top, so we're using the specific heat of steam. All right, so let's do that. Q is equal to, again, 50 grams times the specific heat of steam is 2.01, and 10 degrees Celsius is the temperature change. That's right here, this little tiny segment. It's not the whole thing, it's just where it ended when it stopped boiling to when you started heating that gas. Or you kept heating. All right, so cancel units. And that is equal to 1,010 joules, which we will convert into kilojoules. And we get 1.01 kilojoules. Okay, I'm going to make a note. Sorry about that. There's that answer here. I'm going to make a note that this is the specific heat of steam. We could also make a note here. This is the delta H of vaporization. Okay, so what do we do with this information now that we know each each line segment? So we know the energy for each segment. We need to add them together to find the total amount of energy or heat that is required to convert this water into steam. And so total, add. So I'm just going to line them up. 6.28, 113, and 1.01. Okay, we're going to add those together, and I get 120.29. Okay, why did I do that? I did that so I can see the sig figs. So remember there's a decimal right there, understood decimal. We're going to draw a line after the least amount of places, which is in the ones place. So my final answer is 120 kilojoules. But we need that significant figure in the ones place, so we'll put a decimal. So this is my final answer. This is the total amount of energy needed. The total amount of heat. All right, so there's an example. There's example 1. I do want to try another. Here we go. How much heat is needed to convert 100 grams of ice? We're just going to go through the steps and not necessarily do the calculation. So it says we've got 100 grams of ice at -50 to water at 85. So again, I'm going to draw my little mini graph. Again, I'm still heating it, or it doesn't have to be perfect. I label 0 and I label 100. That's first. Definitely memorize those. Then I'm going to come in and say, okay, it's starting at -5, which is just below, but we're going to put it right here, -5. And then we're going to 85. So 85 degrees would be about right there. Okay. So we're starting here and ending here. So let's see how many segments that's going to take up. Okay, so that's 1, 2, 3 again. So let's just go over what steps are we going to use, and what are the temperature changes here. So from here to here, that's going to be 0, because that's where that line starts, and we can put as many places as we want afterwards, minus -5.0, and that's going to be actually a positive change in temperature. So it's going to be 5.0 degrees Celsius. All right, this little segment here is 85 is the final, minus 0 is 85 degrees Celsius. And notice these temperatures are both positive. They're increasing in temperature, and that makes sense because we're heating it. It shouldn't have one where you have a decrease and the other where you have an increase. So if that happens to you, check that out again or ask me a question on it. So line segment 1, it's a diagonal, so hopefully you know you'll use Q equals MC delta T. Okay. Line segment 2 is a flat line, a plateau. So line segment 2, we will use enthalpy stoic. And line segment number 3, we are going to use diagonal, so that's Q equals MC delta T. Okay. And then our last step would just be to find the total. A couple things I want to make sure that we've got. What specific heat am I going to use in this equation? So I'm right down here. I'm in the solid region, so I'm going to use C for ice. For enthalpy stoic, where am I? Am I in fusion or am I in vaporization? I'm in fusion. So I'm going to use delta H fusion. Okay, and then you have Q equals MC delta T, the next one. So that's right here. That's in the liquid region or water. So that's going to be the specific heat of water. All right. I know these problems look kind of scary at first, but as you do them, you'll get used to them. They'll actually be fun little puzzles that you can finish solving, even though they take multiple steps and 18 minutes to do.